söndag vid lunchtid den 22 mars 1998 när SK 1046 är på väg till Kiruna med närmare 100 passagerare ombord. En rutinmässig flygning, men helt plötsligt inträffar en dramatisk händelse.
Vi var 20 minuter innan landning och hade så smått börjat planera nedgången mot Kiruna. Då en av kabinpersonalen kom fram och sa att det luktade väldigt mycket av brand ute i det främre köket. Och vi startade felsökning och åtgärder direkt genom att slå av strömmen till köket och sen försöka leta reda på det som eventuellt kunde vara orsaken till den här stickande lukten då.
Kaptenen beslutar att landa planet fortast möjligt. Några av hjulen exploderar vid den kraftiga inbromsningen, vilket ytterligare förstärker den dramatiska situationen. Man beslutar att evakuera passagerarna genom nödutgångarna. Som alltid när det har skett ett tillbud med ett trafikflygplan kommer Statens haverikommission att undersöka tillbudet. Syftet med den utredningen är att öka flygsäkerheten och förhindra att liknande olyckor inträffar i framtiden. Det moderna säkerhetstänkandet inom trafikflyget inleddes på 50-talet med de första jetplanen som kunde flyga både högre och snabbare än tidigare. Men olyckorna var många och flygbolagen insåg att säkerheten måste förbättras kraftigt om trafikflyget skulle ha en framtid. Idag har riskerna reducerats till knappt 1,5 olycka per miljon avgångar, som är en mycket låg olycksfrekvens. Men under de senaste 25 åren har antalet olyckor varit nästan konstant, trots att det har skett en teknisk utveckling.
If we don't improve the rate, we are going to have far more accidents, even though the rate remain the same, because the number of hours flown will go up. But the main problem still remains the human factor. And the human factor is not just the individual, but the human within the system. So we're looking at things like training. For example, one of the recent Boeing studies showed that the failure of the flying pilot to follow standard operating procedures is a problem in the majority of accidents. And so we're now looking at why is it that this is happening? Is it cultural? Is it training? Is it documentation? Are the procedures not good enough? So all of that sort of work is going on to try and identify why that is the case. But primarily it's the human factor, but the human within the broader system.
Bassi är ansvarig för utredning av alla flygolyckor i Australien och hit rapporteras årligen över 5 000 olika incidenter och närmare 300 flygolyckor. Idag är en stor del av verksamheten inom Bassi inriktad på ett förebyggande flygsäkerhetsarbete, vilket innebär att man analyserar vilka fel och brister hos människan, organisationen och i de tekniska systemen som kan utvecklas till risker för flygsäkerheten.
Okay, what have we got?
I laboratoriet kan utredarna undersöka olika delar från havererade flygplan.
From the piper. This is the propeller?
That's actually tip of the propeller over there, and we have part of the wing from the another aircraft. And what is quite interesting, if you look at that...
What we're looking at is understanding why components and aircraft structures fail. The difficult thing is to understand why something's broken. We need to initially go through and work out the sequence of failure, but when we come down to finding out the thing that first broke, why did it happen, and understanding the engineering safety system behind that, going into those things, finding out the root causes. Once we find out the root cause, we can prevent failures recurring.
So how do you do it?
A lot of it's just using creative thinking, understanding, looking at physical evidence. So we're looking at fractures, any other little marks, telltale signs, and we're using everything from visual to stereo light microscopy through to scanning electron microscopy, just to give us an idea of all the little detailed features. This engine failed in a catastrophic manner. The thing that happened, there's a number of components that failed. Connecting rod cap broke, the connecting rod bolts broke, counterweights broke. There's considerable damage. So the key thing is to go through and sort out the sequence of failure. So we came down, carefully examining all of the fractures and established that this circlip was the first to fail. The fractures on here identified as fatigue failures. That means that they've been caused by repetitive loads during operation. To establish this for certain, we can take that and examine that at higher detail in a scanning electron microscope. In the scanning electron microscope, what we're looking for are the microscopic features which conclusively identify the mechanism of crack growth. Once we can identify the mechanism of crack growth, then we can look at the reasons why that crack's growing. So in this case, we're looking at the dynamics of the engine more as a major contributing factor to this failure, rather than a fault in the material itself.
What are the largest or biggest threats against better air safety?
I think probably the biggest threat is complacency. That people think that because the accident rate is already very, very low, and has been so for a long time, that maybe we should relax a little bit. But as soon as you relax, then you're in danger. People have to understand that safety is dynamic, because aircraft operational environments, technology, political situations, regulations are all changing all the time. And it's important to look at the impact of all of those changes on safety and determine how it's going to affect us and work out ways to combat that. If we don't do that, then the accident rate is likely to go up. So we not only have to try and reduce it more, but we have to make sure we keep a cap on what we already have. And part of that is sharing information internationally. It is very frustrating in accident investigation to find that an accident may occur through reasons which are well known but had not been passed on to that particular airline or operator.
Med hjälp av modern teknik som robotarmar och undervattenskameror är det idag möjligt att undersöka havererade flygplan på havsbotten. Här har man funnit den så kallade svarta lådan som de flesta flygplan är utrustad med. Om informationen är oskadad så finns uppgifter i lådan om vad som har hänt under den sista halvtimmen före ett haveri. Och det kan många gånger vara just den informationen som en utredare behöver för att kunna förklara orsakerna till en olycka.
Well, the cockpit voice recorder, as the name suggests, provides information on the audio signals in the cockpit. Obviously the crew's speech is the most important, but it also records background sounds, any switch movements or lever movements on the flight deck, and any oral alarms that go off. As well, you can hear background sounds such as the airflow noise or engine noise as well.
Okay, in order rotation this time. Rotor RPM 100%, airspeed 100 knots, passing 3
We can analyse those background sounds, and if necessary and the background sound is there, we can get valuable information sometimes. The flight data recorder records aircraft parameters, things such as altitude, airspeed, heading and so on. And modern flight data recorders can record over 600 parameters. So on a modern Airbus or Boeing aircraft where there are digital data buses on board, it's easy to tap into those and record a lot of data.
I en dator kan siffrorna omvandlas till bilder som ger utredaren möjlighet att visuellt analysera ett händelseförlopp.
With this system we can do computer graphics animations of an incident or accident, and this shows the runway coming into sight and the crew landing on runway 24. Landing at a high pitch altitude and it scrapes its tail. We can stop the animation, we can rewind it in effect, and we can pause on the area of interest.
The problems in many accidents is the failure of pilots to follow standard operating procedures. The question we need to ask now, and what is being asked, is why is that the case? If the procedures are there and they're perfectly good, why are they not being followed? And that is one of the key areas of endeavour, to try and understand why it is that pilots deviate from these procedures.
Vid Tekniska högskolan i Stockholm pågår forskning som kan ge några svaren till hur samspelet mellan människa och teknik kan förbättras.
Om man tänker sig säkerhetskritiska människa-maskinsystem där man har en operatör som övervakar processen. Så när någonting går fel så får man ju varningssignaler i form av ljud och även bilder då. Det är vanligast med bilder och text och lampor. Men det kommer väldigt många ljud också. Och det är ett sätt att kommunicera med systemet mellan operatören och systemet. Och som en del i att minska risker i tekniska system så måste den här kommunikationen fungera. Tanken är att de ljud som används idag, de hörs mycket väl, för väl. De distraherar i många fall snarare än att hjälper, och det är där problematiken ligger då.
Vi har ju intervjuat många piloter i undersökningen och samtliga säger ju att det är ljudsignalerna, de är för många, de är för långa, de kommer för ofta, de kommer vid fel tillfälle. I en nödsituation om man verkligen behöver möjlighet att sortera information så kommer allt på en gång. Det de gjorde i Gottröra, det var att de försökte bortse från den här mängden information och koncentrerade sig på flygplanet, glidflygplanet ner.
Min hypotes är ju att olika ljud påverkar prestationsförmågan negativt. Alltså att den försämrar prestationsförmågan. Så att man vill ju störa så mycket att man riktar uppmärksamheten åt det som är väsentligt. Men man vill inte störa så mycket att det blir distraherande. Och den här balansgången och att välja för- och nackdelar, det är det som är ingenjörskonsten i det hela.
Kan det vara brist på kunskap som gör att det fortfarande ser ut som det gör?
Ja, det tror jag definitivt. För att när vi har börjat med det här projektet så säger man dels på Boeing och dels på Airbus att vi vet för lite om det här området. Det vore väldigt bra om man fick mera kunskap på området.
University of Manchester i England. Här vid den psykologiska fakulteten forskar och undervisar professor James Reason. Hans forskning om riskhantering har lett fram till en modell för hur man kan öka säkerheten i komplexa tekniska system som till exempel kärnkraftverk, kemisk industri och inom flyget där konsekvenserna vid en olycka kan bli katastrofala. James Reason menar att riskmedvetandet måste öka inom företag och organisationer.
There is no way we're going to change human fallibility. Human error is part of the human condition. We're not going to change the human condition. And it has to be stressed that errors are not intrinsically bad things. Errors represent, if you like, the edges of the runway light. They tell us when our performance is beginning to fail. In other words, they give us the pathway towards correct performance. They are essential part. Trial and error learning is the only way we can cope with novel situations. One of the central questions in understanding technical risks is how do we model organizational accidents? That's the kind of accidents that happen to complicated high technology systems. Now, most technologies understand the nature of their particular hazards. And so what they do is they build defenses. And they build often several defenses, separating the hazards from the possible victims, the damage and the losses. And these defenses are of many different kinds. Sometimes they can be engineered safety features like signals on a railway track, or they can be automatic shutdowns as they might be in nuclear power plants, or they can be high technology automation as in modern aircraft. But they can also involve people. And in fact, people often turn out to be the most important defense. So pilots, control room operators in nuclear power plants, train drivers, in a sense represent the last and most important line of defense. But in between there are all kinds of other sorts of defenses. There are administrative procedures, there are controls, there are regulations, And there are trainings and briefings, standards. There's a whole range of these different kinds of defenses. And these are defenses in depth, and this makes it very unlikely that these hazards would ever come into direct contact with victims, assets, and people. So let me show you how such a system might be. In an ideal world, we would have a system like this, where each of the layers of defense, one behind the other, is intact. They are truly redundant because there's very little opportunity of anything penetrating down through these defenses. But in the real world, they are actually more like this. They have holes in. And now we can begin to understand the character of an accident. Many times we have defenses that are penetrated just once. One defense and it's stopped by the next. This is a free lesson. It's a very low-grade incident. On other occasions we can have incidents that penetrate several defenses. Maybe as many as 3, but again, they're stopped. This is a more dangerous incident. It would certainly become studied in some detail, but once again, the defenses worked. On very, very rare occasions, however, we get these holes lining up. And I should point out that the holes are not, as they are in this piece of wood, static. They're actually moving around. They're changing their shape, they're changing their location. But once in a while, we get a situation where we can actually have an accident trajectory that goes through all the different defenses. And so, on these rare but often catastrophic occasions, we get hazards coming into direct contact with victims. And the question is, how do these holes appear? Well, there are really 2 kinds of holes. There are the holes that the operators put in, the people who are the controllers of the system, the pilots and the train drivers. They can make errors or they can commit violations, and they open up holes very briefly. And these are what you can call active failures. They're made by people at the sharp end that have a direct impact upon the system. But there are other holes which are actually, in some ways, more dangerous because they last for longer. And these are due to latent conditions. They're like latent pathogens in the human body. They are problems that have been created by top-level managers, by designers, by manufacturers. They didn't intend to create these problems, but they are inevitable. That there are some deficiencies in structure or in design or in procedures, and these lie dormant, doing no particular harm often for many, many decades, until a particular set of circumstances combines them with local events to create this trajectory of opportunity. And this is one way of understanding the kinds of what I've called organizational accidents that happen in complex technologies.
James Reesens forskning tillämpas vid bland annat flygsäkerhetsorganisationen BASI, som anser att det är viktigt att publicera aktuell forskning om flygsäkerhet och teknisk utveckling.
In this issue of Asia-Pacific Air Safety, we'll look at BASI operations and Rod Fearon's article on Swissair 111.
In the information section of the Bureau, we are very proactive in the way we release information. We're looking at the media, the public, the aviation industry, and it's a crucial role, I believe, in the Bureau to get the information out to these people. We disseminate some 400 or 500 reports each year. We have a very proactive internet site that is growing daily, putting a lot of emphasis on that. But predominantly our work is done via the telephone or sending out hard copy reports to the people.
The breakdown of separation was between a 747 and...
I Australien kan också vem som helst och helt konfidentiellt skriva och fråga om eller anmäla en flygincident.
We receive a range of reports from pilots, air traffic controllers, maintenance people, cabin attendants, just about anyone in the aviation industry, and even at times from people in the community, travellers, passengers on aircraft. And the aim of the confidential program is to A, obtain information about I did this, I learnt from this mistake that I made, or I learnt this from this experience. And secondly, B, we have the information that people may not otherwise report to us, and so it's a way of capturing information that people may be reluctant to report to us through any other system. And from these reports we can add to our safety benefit to the community.
When there are very, very few accidents, as there are in these high technology systems, we no longer know where the edge is. We no longer know where the dangers are. And so one of the really difficult tasks is to make people conscious that they are still at risk. And one of the ways in which one can influence all the defences, and perhaps the only way you can influence all the defences, is by creating an adequate safety culture, because it's only culture that reaches into all the parts of the system in the same way as the defences reaches into all the parts of the system. And it's within that culture that we would hope to build in this sense of chronic unease, the sense of vigilance.
Well, my interest in aviation safety began when I obtained my commercial pilot licence. At that time I became increasingly aware of the limitations of humans. Statistics continue to indicate that over 70% of accidents and incidents can be attributed in large part to human error. And what I believe we need to do is to work proactively to ensure that our aviation system can effectively manage that human error. We're trying, in relation to proactive safety, change people's attitudes about the way they think towards safety. It's been very traditionally reactive in that we've learned some very hard lessons, but we've learnt those lessons after the fact, after an accident, after an incident. It might not simply be because somebody chooses not to follow the rules and do everything as advertised. It may be that those defences in themselves, crew resource management, correct maintenance, following standard operational procedures, it may be that those defences in themselves need improving in the first place. And that's what we're trying to encourage the staff in an organisation from bottom level right up to top level to actually critically evaluate those defences and see if there's a way ahead to make them even better than they possibly are at the moment.
Cirka 15% av alla flygolyckor beror på bristande underhåll och skötsel av flygplanen. Dåliga kunskaper, trötthet och slarv är några av orsakerna. Men Alan Hobbs, som är psykolog vid Bessie, menar att det inte är människan vi i första hand ska ändra på.
We don't try and change people, we try and change systems or the organisations that people work in or the way they do their jobs. A lot of the incidents, the little everyday problems that happen in maintenance don't get reported because people are fearful, they're afraid they're going to lose their jobs or get into trouble or have a note put on their file, or in some companies they'll lose money, they'll have their pay deducted because they've made a mistake. We need to learn about what's going wrong, and we only will learn about it if we can encourage people to tell us about things that go wrong. And the present system, unfortunately, seems to discourage people from reporting incidents. It seems to encourage people to keep quiet when things go wrong and just correct them.
With the company here, we use a double check system where a certain block of a service or an inspection's carried out, and then there'll be somebody else come along and have a look at that section of the aircraft before it's closed.
We can't wait for accidents or incidents to find out we have a problem. We have to bring in programs to identify the areas where we are weakest and attack them before they contribute to accidents or incidents.
So you think it is possible to lower the rate of accidents?
I think the evidence of that is quite clear. There are operators who have been operating for many, many years without having any accidents at all. So to say that a zero accident rate is an impossibility is in fact wrong, because plenty of operators around the world, both in Australia and overseas, have shown that you can operate for many, many years without having accidents or incidents.
Tillbaka till den svenska haveriutredningen där man nu ska undersöka orsakerna till rökutvecklingen på SAS-planet.
Rökutveckling i kabinen under flygning, det är alltid allvarligt. För man vet ju i det läget inte vad orsaken är. Och nu visar det sig att i själva verket så var det en ganska banal grundorsak. Det var ett tekniskt fel, men ett väldigt litet sådant. Men det faktum att det gav den här rökutvecklingen som skulle kunna varit något mycket, mycket allvarligare, skulle kunna utvecklas till en katastrof, så sätter det igång en utredning som vi då gör. Samtidigt så tar vi tillfället i akt att testa systemen som finns. Hur ser instruktionerna ut för teknikerna? Är de relevanta? Är de korrekta?
Det är någonting som ser konstigt ut.
Vad har piloterna att följa i en sån här situation? Så vi har ju ägnat en hel del tid åt att se då på deras instruktioner. Vad har de att följa i det här fallet? Och där hade ju vi från haverikommissionens sida ett antal frågetecken. Det är inte helt lätt att följa de instruktioner som de har, de nödchecklistor som de har. Och det är det läget som vi också tyckte var viktigt på mötet att diskutera med de berörda, både piloterna och de som är ansvariga.
För våran främsta koncern var ju att få ner flygplanet så fort som möjligt. Jag ville inte riskera att vi skulle hamna någonstans halvvägs klar med en nödchecklista.
Den process som har satt igång gör att man lyfter på ett antal stenar som kanske inte har lyft på tidigare och som förhoppningsvis leder till åtgärder, information, kunskap som i sin tur ökar flygsäkerheten på sikt.
So we are now facing a rather paradoxical situation where we might have to ask the question, are accidents necessary for safety? We have them very, very infrequently, but if we didn't have them at all, or if we go for long periods without them, we know that organizations begin to forget about dangers. It isn't in human nature to think all the time about the bad things that happen infrequently. Culture, certainly in the late 90s, seems to be the central issue. How can we engineer a safe culture? That's the challenge for the millennium.